Hello, my name is Hussein Adalati, and I'm a PhD student in the Department of Biological and Agricultural Engineering at UC Davis. Advised by Professor Rohang Zhang, and I'm presenting our work funded by the CDFA, the California Dairy Research Foundation, and the Almond Board of California on the production and application of compost products from dairy manure and almond waste as soil amendment on California almond orchards. In 2020, the top two agricultural industries in California were the dairy industry, which generated $7.5 billion, and the almond industry, which generated $5.6 billion. Both these industries face challenges. Dairies produce lots of manure in a small area, contributing 25% of California's methane emissions, while 13% of the harvest brought to almond processing facilities is field debris, including sticks and twigs, which have little to no value and present several challenges. One potential solution, and the goal of this project, is to recycle dairy manure and almond stick and twig waste back on almond orchards as soil amendment in the form of loose and pelletized compost products that are nutrient-rich, safe to use, sequester carbon, and provide economic and sustainable benefits to the soil, crop, and environment, creating an almond dairy loop as pictured in Figure 2. These industries already have a history of synergistically working together and geographically overlap as shown in Figure 1. Ultimately, dairies need to export manure sustainably, economically, and generate revenue streams. Almond orchards need organic matter amendments to build healthy soils, and as a society, we need to reduce our GHG emissions and sequester carbon. Figure 3 is a flow diagram that summarizes the project. Dairy manure and dairy manure mixed with almond sticks and twigs were composted to create treatments 1 and 2. Some of the loose composts were pelletized using a flat die pellet mill to create treatments 3 and 4. And in addition to the no amendment control were the 5 treatments in the orchard studied. Manure for composting was generated from a solid liquid separator system as seen in Figure 4. Figure 5 shows side and front views of the compost windrow setup. Windrows returned weekly for 8 weeks of active composting. Process temperature was monitored during this time. By regularly measuring compost physical properties and pile dimensions, we were able to monitor changes in the windrows over time. Figure 7 shows that the manure-only compost pile achieved a temperature of 70 to 75 degrees Celsius in the first 4 weeks of composting and then dropped as moisture in the pile dropped. Figure 6 shows reduction in compost total solids, volatile solids, and moisture by 36, 62, and 88% after 8 weeks, respectively. Manure stick compost piles had similar results. Figure A shows the lab scale pellet mill used in this project, and Table 1 shows the moisture content of manure-only compost and pellets and a doubling of bulk density after pelletization. Products were applied in the orchard in March 2020 and February 2021. In the right panel, Figure 9 shows a rear view of the tractor pulling the applicator as it applies products. Products were applied at a rate of 4 dry tons per acre in a commercial almond orchard. Table 2 shows loose and pelletized product composition. The NPK added to the orchard when applying 4 dry tons of product per acre were 100 pounds of nitrogen, 28 pounds of phosphorus, and 72 pounds of potassium for the manure-only treatments, and 84, 18, and 60 pounds for the manure stick treatments. Figure 11 shows the experimental layout, and Figure 10 shows 2021 yield data following 2 years of product application. Data has not been analyzed for statistical significance, but there do not seem to be differences between treatments. One issue that comes up with applying amendments on orchards is that the harvesting process cleans the orchard floor and removes any amendment still there, limiting the potential long-term benefits of organic matter amendment application. Thank you, and I hope you enjoyed this presentation.